Welcome back to this module about an introduction to optimal decision making. And in this section, we will focus on how to compute an optimal threshold, in particular in the binary case. We have seen already how we can calculate the expected cost of making a prediction by marginalizing basically among all the possible true classes basically. And here what we will do is basically select which is the optimal class, or the selected class is the one that minimizes the expected cost of each of those predictions. Then in the binary case, we want to predict class 1 if and only if predicting class 1 has a lower expected cost than predicting class 2. Very simple. Then here we show what is the expected cost of predicting class 1, which should be lower or equal to the cost of predicting class 2. Here we have decomposed this summation into the two elements, class 1 and class 2, the true class 1 and class 2, and the cost of the correctly classifying class 1 and classifying class 1 when it is actually not class 1. We can realize here that there is an equality, and exactly in the equality, they both costs are the same. It doesn't matter which class you predict. Then here we are just looking at what is the actual probability that makes this expected cost the same in both sides. I simplified the posterior probability of class 1 given x to this small p, and 1 minus p is basically the posterior probability of class 2 given x. Then we will select class 1 if the posterior probability of class 1 given x is lower, bigger actually than this threshold that we are going to look for at the here. Then just following this derivation, we can find out that this optimal threshold can be computed directly with these values from the cost matrix. Then from this simple cost matrix and applying the equation that I have shown in the previous slide, we can find that the optimal threshold is 0.5, which is the most common scenario in which all the costs are the same in a binary case for both classes. And yeah, and then the posterior probability, when the posterior probability of class 1 is bigger than 0.5 or equal, then the optimal decision is selecting class 1. What happens with different cases? This is an example in which the diagonal is not 0, which means that we have actually gains, because those are negative costs, which can be seen as gains. And I actually choose to have a higher gain for one of the classes than the other one. And how would the cost lines look like? This is basically the figure for the cost lines. Then in this case, if we get a new sample and we predict that the posterior probabilities are 0.4, 0.6 for class 1 and class 2, then we can calculate the expected cost. If we predict class 1, it will be minus 1.4 cost, which is a gain of 1.4. And if we predict class 2, this will be 3.4. We can see these 2 points in 0.4 for positive class, which is this posterior probability of class 1, which corresponds to predicting class 1, this point here, which I indicated that it was minus 1.4, and predicting class 2, which is 3.4 as indicated here. Then let's look at other cost matrices. Here the cost matrix is shown in these 4 elements: the cost of the true class 1, cost of the true class 2. This is basically if it's the previous matrix basically. Then notice that the cost of true class 1, which is -5, corresponds to this point here, which is the cost of predicting class 1 given that it's class 1, and because here the posterior probability of class 1 is actually 1, means that it will always incur into this cost. If instead we predict class 2 and it's for sure class 1, then we will get this 10 cost, which is this cost of false class 2. Then similarly on this side with the other two. Then we can play around with these values, and let's put this class, the cost of predicting class 2 given that it's 1, let's lower it down and let's make it very low, like 1. What we will see now, this now has moved to 1, and we can move, and the threshold has moved accordingly. And let's move things a bit around. Then, for example, let's move this down, which is the cost of predicting class 2 when it is class 2. This is the cost of true class 2. And we can see how the optimal threshold just changes. Then in this example, we see that the optimal prediction, basically all of the threshold, doesn't change if the cost matrix is multiplied by a positive constant value or shifted by a constant value. And in this example, we have a fixed cost matrix, which is this one, but then we will shift it with I just assign -10 to +10 and multiply it by a constant value m. Then we will see that the threshold is still 0.8 here, and the expected cost is the only thing that will change. For example, if we shift by 10, the only thing that will change is basically the scale of the expected cost. The threshold will remain the same. We can multiply by 20, and the same, all the costs are modified accordingly, but the thresholds are fixed. Here we can see the resulting matrix. Then it is possible to simplify the cost matrix. Basically, as I said, the optimal threshold of the optimal decision will not change if we multiply the full cost matrix or if we shift it. If we multiply by a positive value. Then common simplification is to ensure that one of the rows has a 0 in the correct predictions and a 1 in the incorrect predictions in the binary case. Then, for example, in the previous example, well, here's an example in which the true class 2, predicting class 2 when it is actually true, has a cost 0, and predicting class 1 when it's actually class 2, it has a cost of 1. This will simplify into this. Notice that we have actually changed the cost matrix to this cost matrix star. I don't show here what is the actual value of these ones. I will show it later. But let's see an example. This is the previous cost matrix that we have seen in the previous slide. Then we can see that if we shift by +7 and we scale it by 1/20, it results in this cost matrix, which follows the what I mentioned here before, and then the optimal threshold will be easier to compute with this new matrix basically. And this is quite common to do. And in this particular case, we can see it in the previous example, shifting by 7 and multiplying by 1/20th. Shifting by 7 and multiplying by 1/20th, we will get the, well, if it loads, yeah, we will get the matrix that I mentioned later, and the optimal threshold is still basically the same. Then that's it with the computing the optimal threshold for the binary case.